This is Learning Assessment Problem 717. In this circuit we have an energy storage element in the form of an inductor and another one in the form of a capacitor. So the problem solving strategy here will be that of solving a second order transient circuit. We're asked to determine the voltage VO of T, which appears across the series combination of a 12 volt source and an 18 ohm resistor. The switch operates from position 1 to position 2 at time equals 0. So an initial determination we might first determine the initial conditions for the inductor and the capacitor. At time equals 0 minus, we'll assume that steady state prevails, and therefore the inductor current, which will be a constant value, is equal to, considering a KVL equation around the entire circuit, this will be this will be 24 volts minus 12 volts divided by 18 plus 6 ohms, and this will equal 0.5 amperes. For the capacitor, we have no information provided. Before the switch operates, it is just connected in an open circuit. So we'll assume the simple condition that VC 0 minus is equal to 0 volts. Now we'll consider time greater than 0. The switch moves to position 2, and we have now a series RLC circuit with 2 DC sources in it. The differential equation which would be applicable here would be a second order I O of T dt squared plus R over L di O dt plus I O over LC is equal to 0. This is the current I.O. in the circuit that happens to be in the same condition as the I.L. at 0 minus. We have a capacitor voltage VC plus and minus, and a resistor voltage V sub R plus and minus, following the passive sign convention for the current direction for I.O. We're going to let I O of T be of the form K e to the st. Then we'll have a series RLC characteristic equation in terms of the complex frequency S is S squared plus R over LS plus 1 over LC equals 0. So R over L is equal to 9 for our circuit, and 1 over LC is equal to 18 from the values of L and C. So our characteristic equation becomes S squared plus 9S plus 18 is equal to 0. And the roots of this are S1 is equal to minus 3, S2 is equal to minus 6. We see that the roots are real and unequal, and therefore our response is expected to be overdamped. So we've used our assumed form here. I_O of t is equal to k1 e to the minus 3t plus k2 e to the minus 6t. The I_O at 0 plus, just after the switch operates, is equal to IL at 0 plus, which by continuity the inductor current is IL at 0 minus, and that's equal to K1 plus K2 from our assumed solution form for the current, and then we just determined that that initial condition on the inductor was 1/2 ampere. So there's an equation in the K1 and K2 coefficients. Now we need another K1, K2 equation. Let's do a KVL around our loop circuit. We have V sub L of t plus R times I0 of t plus 12 volts minus 4 volts plus VC 0 plus Vc of t is equal to 0. We've decided that we need another equation to solve for the K1 and K2 coefficients. So let's look at the Kirchhoff's voltage law summation of voltages around our existing loop. Now we have VL of t plus R times I_O of t plus 12 volts minus 4 volts plus Vc of t is equal to 0. This is for time greater than 0. At t equals 0 plus, just after the switch operates, we have VL at 0 plus plus RI0 at 0 plus plus 12 volts minus 4 volts plus Vc at 0 plus is equal to 0. Now we said we assumed the initial condition on the capacitor was 0 since we had no other information. So we'll drop that out of the equation. We have an I0 at 0 plus. I0 at 0 plus is equal to IL at 0 minus by the relation of I0 and IL are flowing in the same direction in the same inductor and continuity of the inductor current. So we can write our KVL equation at 0 plus as VL at 0 plus 18 times 0.5 amperes for the RI0 term plus 12 volts minus 4 volts is equal to 0, or V sub L at 0 plus is equal to minus 17 volts. V sub L of t is equal to LdI Ldt. In our case, the inductor current and the I0 are the same, so this is LdI0 dt. And this will be 2 henries. Differentiating our assumed form of the current I0, we have minus 3 K 6k1 e to the minus 3t minus 6k2 e to the minus 6t, or for the specific situation VL at 0 plus in time, the exponential components will go to unity, and we have that VL at 0 plus is equal to minus 6k1 minus 12k2 is equal to minus 17 volts from our VL at 0 plus analysis just above. So we can put the coefficient information into a matrix equation format. We'll have 1, 1, minus 6, minus 12, K1, K2 is equal to 0.5 ampere and minus 17 volts. And we can solve this for the K1 and K2 terms. This is equal to minus 1.833, and K2 is equal to 2.333. So I0 of t is equal to minus 1.833 e to the minus 3t plus 2.333 e to the minus 6t amperes. This is valid for t greater than 0. And then our VO of t is equal to R times this IO of t plus 12 volts from the series 12 volt source. So VO of t will equal 18 IO of t plus 12 volts for t greater than 0. The resistance value R was equal to the resistance was equal to 18 ohms in the circuit.